Hello guys, I'm sure you're doing awesome. So today we are back with another video which is one of the very important concepts when we are doing our queries and when we are scaling our database and when like a little more data or a data intensive application when we are facing, there are some inevitable concepts that we must know as application developers. And among those concepts, the most important is the concept of the indexes. But before going to index, we will gradually touch upon a lot of things. For example, the heap storage, how the data is being sorted, and how exactly the indexes help, so that we will gradually build the intuition that what exactly indexes are, rather than directly talking about the clustered index, non-clustered index, and whatnot. We will try to take some use cases and gradually build our understanding. So let's take a use case of Amazon product search. Okay. So what happened during Amazon product search is, like, you have a full catalog of products, and out of that you are going to search whatever the product you need, right? So over there, like in our search box, suppose we are putting something like a wireless earbuds. Okay. Now, what it means is the system must do few things, like it not only have to retrieve. So retrieve is definitely the first thing that it has to do. After that, it has to rank them as well on various filter. For example, you might see things like which are the sponsored one, or very high ranked one. So this way we could see that it is not a very straightforward thing like only selecting them. After selecting, we have to do some sort of a ordering as well. So let's see what are the fields generally, like when we are searching something like wireless earbuds, what are the fields it generally returns. It will return fields like product ID, title, then price, category, is sponsored, average rating. Like when we do a select query on top of it, these are the things we get, right? Now, where exactly Amazon, like for their backend, stored this data? They store this particular data, something called a heap. Now, again, as I always say, computer science engineers are very bad in naming things. This heap doesn't really have anything to do with the actual heap data structure that we are aware of. Okay, so this is just an unordered collection of pages. So we will come a little bit more into this understanding. So what heaps are in this case, like you can say that there are number of pages like page 1, there are page 2, page 3, etc. All these things are collectively, like if I can see that this is page 1, and then this is like page 2, this is page 3. So all these things are collectively can be said like they are being stored into the heap. Okay, so this is, as I again said, like has nothing to do with the heap data structure. So suppose each page is of 8 kilobytes, and it contains multiple product rows. Like for example, this page 1, suppose it contains like 1000 rows. Okay, similarly in 8 KB of size, it also has 1000 rows. This also hold 1000 rows. Okay, so in 8 KB of each page size, it keep on holding this. And also I hope you have seen my previous video there. We have discussed what exactly is DB pages are. Like there we have discussed a very important concept. DB pages are not OS pages. So this paging concept that we are talking about here, this is a very important thing to note, that DB pages are never really OS pages, right? So coming to this, uh, we must understand that any new product that are being inserted, they will be like, if the page is generally coming from the operating system, and then database creates its own page hierarchy. And when the 300 like here total 3000 records are there, right? If I sum it up, how many records are there? 3000. Now suppose for some reason this records are being completely saturated, like this page 3 is being done. So where does the 3001th record will be stored? This particular record will be stored in page 4. Okay, so this particular record will go to page 4. As simple as that. A new page will be created. So this particular thing we have discussed in previous video also, but just doing a small revision was important. In case you want to understand in much more details, please see the previous one. All of your concept will be clear over there. So in this context, let's talk more about heap. Okay, this is something that we have to understand before understanding the details around the uh, indexes. So what let's at first understand what heap is not. So heap is not the OS heap memory or the heap data structure that we are talking about. Okay, so it is not OS heap memory nor heap data structure that we are talking about here. Okay, so generally in the OS heap memory is nothing but a region of the process memory that used for dynamic allocation, right? Like for example, when we do like in C a malloc sort of a thing, or in C# or Java we do new, it gets the memory from the heap. Again, these things were covered in very detail in our operating system videos. So this heap in database internals is a unordered and append optimized physical storage data structure for the table data. Okay, so heap is append optimized, and so heap is nothing but a append optimized and unordered physical storage structure. And so when the table data are being stored in pages, this is kind of a collection of pages, right? This is simply a collection of pages that store rows in a insertion order. So if like these are different pages, like page 1, page 2 and page 3, we can say that heap is actually holding these pages, this collection of pages. Okay, and there is one more important thing, it is unordered. Okay, this is unordered. This is very important thing to understand, that there is no order into this particular data. So why I'm emphasizing on this unordered, when we gradually come into indexes it will be more clear to you. So think of it as just a pile of papers. Okay, and you add new one on top and find new one, and you might have to flip through the whole stack. Like for example, here all my rows are there, right? Here my rows are will be like here, all my rows are here. So to get this, guys, what I have to do is, suppose to come to this particular record, I have to flip through all the pages. There is no particular order is being maintained. So uh, now let's understand this part a little bit more clearly about the unordered data with an example now. So this is the logical view, what you see or we see as a developer, like while we are creating a table. Suppose create table products, and then we keep on inserting the sample rows. Okay, so here you see there are few sample rows we have presented. Now what we have searched earlier, if you remember, through our select query we were trying to search the wireless earbuds. Okay, so in our Amazon search, so you see there is this wireless earbuds over here in our title. Now uh, for this particular record, let's see how the paging is being done. So then we will see for a given search what exactly happens behind the scene. Let's do some calculation over here. So suppose each page that we have, okay, so the pages that we were talking about, so each page size is very limited, somewhere around the 8 KB. Okay, the page size is somewhere around the 8 KB, and each product row, like this particular row I am talking about. Okay, so here this is a row, this is also a row. So over there, the each product row is around 200 bytes. Okay, This is again some kind of an assumption that I'm trying to make. And suppose going by this calculation, there will be around 40 rows per page, right? So how the pages does look like? So pages would look like something like this. I will just try to give you a structure. So the page 0, for example, the first 8 KB will be somewhat like this. Like there is a header, there is a row count, and you can see there is a product ID, title, everything will be here. Okay. So there are 40 records are there, and there are also 41 to 80 records are in the page 1. And similarly in the last page probably there is close to like 100,000 records, right, or more. So those rows will be inserted in our last page. So each of this has around 40. Okay. So each of this have around 40 per pages into this. Like this has 40, this has 40. This might be having a little less, but like it will keep on getting appended. And why we call it heap? Historically, like this is just a heap of record, right? All the pages, like page after page, as we discussed earlier, are being stored into a memory heap. Okay. Like this term even predates the modern priority queue sort of a thing, or the heap data structure that we were talking about. Now let's see um, that we have understood two concepts right now, right? Like what exactly is a page is. Page we understood from our previous video, what exactly DB page is, and what exactly the database heap is. So pages where the rows are getting stored in a unordered manner, and heaps are basically the place, the collection of those pages. Okay. Now how queries would work on a heap? So let's talk about this simple query. Like I do a select star from products where we have this particular column of title. So what I will give is where title, like something like earbuds. Okay. Title like earbuds. So what it will do is it will at first start at page 0, right? It will start looking at the page 0, and it will say whether in page 0 any earbuds is there or not. Then it will go to the page 1, then it will go to the page 2, right? So the process that the the scan of the database goes like this. Like the DB engine would start at page 0, then it read entire page, right? Because it doesn't really know where exactly this like it have this particular page, and the entire page, to read it, it has to bring it to the buffer pool, right? So buffer pool, again, I hope you remember it from our previous video. So there is a operation that it has to go through by bringing all the data to the buffer pool. Okay. So after buffer pool, what happens? After buffer pool, it will try to see whether the earbuds is present there or not. Then again it will move another page, like after page 0, the same operation it has to do for the page 1, similarly for the page 2, and in this manner it will keep on doing it for the page n. So you can see this is a form of like a this is a form of flow. It keep on repeating after n plus 1, and total how many IO operations it has to do. Like if I have to find the number of IO operations, the number of IO operations will be n plus n. So like if it has like 2 billion products, so for searching earbuds, Amazon has to go through full product catalog. Like if it has 2 billion product, like the full scan it has to do. So probably you understand the complexity now, that if we are just keep on storing the data like in a good old manner that we keep on like just throwing the data into our heap and into our page. This is the kind of thing might happen. So here what we can do, if as a developer, suppose you don't even know that there are some solution exist, if as a developer this comes to you, that dude, how do I solve this problem? Because I do not really want to go through 2 billion records just to get, for example, like how many, probably 2000 earbuds are there. Just to get them, I do not really want to go through 2 billion records, and it would be pathetically slow, right? So if as a developer or as a engineer you have been asked to solve this problem, you will definitely say that let's solve this problem in a way that let's introduce something like a reference store, where I'm going to store all the references of this particular products. For example, all my references of wireless earbuds, or maybe only for the wireless, I'm going to see that how many pages are there, like it is in the page 1, row 6, something like that. Okay. And earbuds are like, there can be so many instances, right? This is only one thing I wrote. There can be like page 86, row 30, 32. Similarly, earbuds are in number of pages, like 1, 2, 3, like this. And then you are going to do a join sort of a thing, and from there probably you can find out all the references. So like as an engineer, to solve this problem, the thing that you would introduce is references for those product titles, right? A separate reference. Like at first I will come to those reference, I will go through all of these things, and then again I will come to my actual page table, right? So there will be an intermediate layer, and this exactly what indexes are, right? So let's revisit the process in a little bit of more organic way. So in general, let's try to understand through this sequence diagram what happens in case of a normal query. Suppose I do not have any kind of optimization. So user over here, they have searched for the earbuds, and from there, this particular select query is being fired, like select star from product, where title like wireless earbuds. The things that we have done earbuds, I am just improving it a little bit, wireless earbuds. Okay. So after that, it has to go through a completely loop sort of a process. So what loop it would go through? Let's see. So at first, it has to get the first page ID, and from the buffer pool, and it will try to see whether that page is in buffer pool or not. Like before, or because this is a completely a select query and all the scan are needed, so what will happen is all the 0 to n pages that we are seeing over here, okay, so all the pages that we see, like 0 to n, what would happen is we are going to get the pages one by one. So at first we are going to hit the buffer pool. Like you probably know that the query engine cannot really directly read from the persistent storage. So any database page, like which are being stored in our this dot table file, okay, so we are going to get from those dot table file from our persistent storage, and we are going to return it into our buffer pool. Then what would happen is the this query engine would go or run a sort of a where condition, through which it would try to see whether there is a match found or not. And if there is any match found for the wireless earbuds, it is going to add to his result list, right? So you can see how expensive this operation is. All the pages, like suppose for billion rows it has millions of pages, all those pages has to be bring into the buffer memory, and from the buffer memory again we are going to do this matching, and after matching this particular result set that are being built by the query engine, this particular result set will be returned to the end user. Okay, so this particular um, like result set are being built on the fly and being returned to the end user. So now probably you see the problem of it, right? The amount of scan it has to do, no real life system would be able to sustain it. So what is the solution? So now let's discuss through this how indexes exactly save our day. Okay, so now I just have created this very basic diagram. We are going to explore the whole process or the whole flow in that. Okay, so over here you see the same query now we have fired over here, like select star from the product where the title is like this. Now if you see, the difference between this particular diagram and this diagram is like there, here we have this B plus tree introduced, okay, or which is the title index. Now why it is a B tree or the B plus tree or inverted tree we call, we will come to that in a later point of time. But for the time being, just understand this index behind the scene, it is a B tree or a B plus tree. Okay, so uh, the moment the query fire, then what happens is it will get the root page of the title index. So we will have the root of our title, or what you can say is something like this, like getting the list of the row IDs. And now what I have is I have all the page numbers, right? So from here, my query engine would ask to the buffer pool, like, do you have the page ID 100 or the page ID 500? If it has, it will already return. If it doesn't have, what it will do is it will get it from our OS file system or our persistent storage by reading this heap file. So it will basically come from here. Okay, this guy will basically come from here, and then again it is going to read only those selected pages, and also it has the slots also, right? So right now I have the selected pages plus the slots where the records are there. So now after getting all of these things, what would happen is, after getting all of these things, we are going to write a intersection. So going back to the simple Venn diagram concepts, I'm not again just assuming that we all have gone through those basic statistics concepts. So then again, just a simple intersection would happen of wireless, earbuds, and Bluetooth and the common records. For example, here you see this is a common records, like wireless and earbuds both are there. This 103, right? This one and this one are a common record. If I have to see, these two are common records. Now what would happen is these two records will be known as, okay, they are the common intersection points and they will be returned together. Now this index traversal is also very fast. Like you might be thinking that how does this index traversal happens? Like it is just an unnecessary complexity sometime in a very crude way if we see. But when we understand the internals of the index, that is why I have written the B plus tree or the inverted, we will understand why the index is necessary. So now at this point of time, at least you understand one thing: when you create an index around a certain row, that particular or a certain column in your table, okay, so suppose you have this product table, and in the title name you have created your index. What would happen is that particular for that particular column, there will be a intermediary data structure will be created. That data structure will hold all the information in this manner. Okay, like for keyword wireless, these are the given row IDs. For the keyword like the, if the title contains earbuds, these are the given row IDs. So by breaking all those things or all the titles, this is how we are going to store our um, indexes, right? So before going into the data structure aspect of it, let's just understand few details. Okay, so let's try to correlate few details. So the heap, page, index, and also there is another important concept, row ID, how all of them come together and used over used to give a very performant query. So what exactly a heap is? Heap is nothing but a unordered physical storage of table rows, right? And then uh, table rows in page rather. Okay, so unordered physical storage of um, rather it should be pages with table rows. Guys, I'm just writing it on the fly, so sometimes it gets messed up. And this is page. Pages are what? Like they are fixed size ones. Generally, like for example, it can be for our case, we have been treating it as 8 KB. Different databases has different kind of size, like it can be 4 KB, 16 KB, whatnot. Then there comes row ID. What is row ID? Row ID is nothing but a pointer to a page. Okay, so that we will come in a little bit later point of time more about the row ID. And what is index? Index is a completely a separate data structure. Okay, so which maps the indexed values to the pages, or rather row IDs. So what happens is, like, all the data that we have seen earlier, like when we were exploring our page concept. Okay, this is the concept we were exploring, right? Where we were treating that there is a page and these pages are being stored in this manner, right? So here we have so many rows, right? So in this case, what happens? These rows are having a unique identifier that is being called as a row ID. So this row ID are very important while maintaining the indexes. So let's see now how indexes store the information. Okay. So let's understand the flow that we have just discussed with a little bit more details and with a more real world data. So now user do this thing, like they have search something like wireless, and from wireless what happens is it goes to the inverted index, or just index for the time being, you just think it with the index. Okay, so what index has? Index has a root sort of a thing, and from root it has all the way the other details, like the wireless are in 5 12, that means it is on the fifth page and the row offset is 12. The earbuds, it is suppose there are multiple places it has, like 5 12. Also it is there in 102 7, etc. Again there are Bluetooth. This Bluetooth is suppose there in the 8 3. Also it is in the 5 12. Okay, so I hope you get the idea. Like there is a root, and how the root is being aligned. We will just go into our next one. So this index, okay. So this index, when the search goes through, what it will return to the like our engine, it will return things like page equal to 5, slot equal to 12, something like that. It will keep on returning. Now the DB engine, so here, suppose uh, it returns this thing to our DB engine. This is just a free flow diagram. I'm trying to uh, explore the whole idea, and then the DB engine would go and fetch the heap page 5 row offset 12, right? So in this way, it will keep on reading the pages from the heap, and once it reads all these things, like from the heap, how it will read is, suppose this is my whole heap is, right? So from the heap is like the page 5 will be read, and then page 102 will be read, like if you have seen, like 102 is there. Okay, so after all these things, what it would do is, to the DB engine, it will return the data. Okay, to the DB engine, if you see, it will return the data, and this is basically like the dot table file. If you see, it is stored internally in the memory like in this manner. So here it is going to return data, right? I hope at this stage it is completely clear to you, like whatever the internals that I wanted to discuss in this particular diagram, that how from the B tree, or how from the products table the data are being returned, and how the query engine is then again fetching all the page plus the row offsets. And this row offsets is nothing but, as we were talking about, the row IDs here. And row IDs basically define each of the place where that particular record is. Now uh, now that the whole picture is very clear to us, let's dive into the extreme internal, that is the relation between the index, the table schema, and the data structure that we were talking about, that is a B tree or the B plus tree. So for example, like whenever we are saving our data, what is the first step? As a step one, like whenever we are going to have our data, the step one always would be to create the index. Okay, so after you do that create table, what we will have is, we are going to create our index on the product, and there will be this title will be created. Now this B tree is the particular structure that is going to hold it in a completely sorted order. So sorted order, suppose it is sorting on the based on the starting alphabets only, or the gradual alphabet movement. So it will be something around this. The B tree structures would look a little bit around this. So the Bluetooth speaker would be at the top, because it starts from the blue. It start with B, right? So it start with B, so it will be at the top of it. And after that, what will happen is, it is B. Then it will be coming to the wired. So again, wired, as you see, like here we have uh, wireless, and here wired. So definitely this thing is coming at first, because D comes before L. So here we have wired, and then on the right side of it, the wireless will be there. So this is how the whole B tree will be done. Now, if I have to traverse through it, right? If I have to traverse through it, you see how easy it is, right? Now, I am just looking for something like a wireless or the wired. So now if I'm standing at the B, I know that I have to go down somewhere for that, because from B, I know which direction the wired would be, right? And to understand it further, there are few B tree basics also. Let me write down for you, so that it will be very easy for you to visualize, in case like you have you need to understand how the datas are being organized. So it's a balance tree, of course, and in that balance tree, the main property is each node can contain multiple keys. Okay, so it is not that like binary tree, only one node will have like two uh, two child nodes. So one single node here can have multiple. Okay, and each node, so so it is basically multiple keys it will hold, and each node multiple childrens as well. Okay, And in the leaf nodes, we have our key pointers, pairs, or for example, where exactly the data is being stored. So now let's start from the root node. For our understanding, I'm going to take the longer route, like writing everything in super detail. So suppose we have a root node. In our root node, I have Bluetooth speaker and smartwatch, something like that. I have Bluetooth speaker, but it contains Bluetooth, so definitely it will return it. After that, where it will go? Like suppose it has, this is its child 0, and in the child 0 it had book 1, book 2, and in that way many other things. Okay, so again the child 1 is going to have Bluetooth speaker. Okay, and alongside this, this is going to store in the leaf nodes. So because this is coming into the leaf node, in the leaf node this is going to store the particular page number and the page row offset, like the row 5. So this is the basic structure of the B tree that we are talking about. So in this way we will keep on getting traversed, and suppose like the child 2, it has something like the S related things, like it has smartwatch. Here it will hold again the page 5 row 2. Okay, then again the exact match, like the wireless earbuds, it is going to hold similar page 5. So in this way, uh, like from here, from in any route of B, it will know like which direction to go, and after getting into that place, it will return this particular page number and the row offset. So with this, probably you understand a very important aspect, that there we can be able to just do binary search in this particular in this particular tree of B tree, and there are very few other important aspects. Like I want you to look up to few things around it. For example, why we are storing the uh, like storing the pointers. When I say pointers, means this data, like the page 3 and row 5, this sort of data in leaf nodes. Okay, so uh, that is the efficiency of searching that comes. So if you just get to understand this thing and understand the B tree in a little bit more details, you will be in a very good position to understand what happens internally. So now that we know about the index, I'm not taking the explaining the full B tree structure, because that's a separate DSA topic or the data structure topic over here, to just discuss around the databases. So just understand this thing, the B tree, in a very organized manner. It keep on storing all the nodes, and like we can just hit any root node, and just by comparing the text we know which way to go. And in this way, in a binary search manner or in a O of log n manner, time complexity, we can come to our actual data, and that increases the like the overall capability of the database manifold. So now let's understand one more important thing, clustered index and the non-clustered index. So right now, if you see, like if a table has what say like 5 indexes, then how many B tree it will form? You just give some thought and then come back, pause the video, and give yourself like few seconds of time. So the thing is that here it will have 5 B trees, right? Why? Because for every single index that is being created in our memory, we have to create for that particular text or that particular number on or particular row value over which we have created the B tree. It has to be exclusive, right? So in case we have like multiple indexes on a table, there will be definitely separate B tree around that. Now each index is implemented in a separate B tree. So if you create multiple indexes, every index, okay, so the concept is every index will have its own B tree, right? Now let's talk about the clustered and the non-clustered index. So every table in terms of the clustered index can have only a single clustered index. It will have only a single clustered index. Okay. And this would hold the actual pointers, pointers to the row offset, I can say. And non-clustered index doesn't hold the pointer to the row offset, rather it holds the pointer to the cluster index. So it might be a little confusing to you, but I'm going to take a very simple example and going to store it, going to show it in a diagrammatically manner so it completely engraved in your mind. So suppose there is for Spotify, okay, for Spotify you have to design the search engine, okay. So how exactly the Spotify would do its search? So the first index that you do, like your index or primarily the clustered index, you have done based on the song ID. Okay. So what happens is like for every song ID, I am aware that suppose there is a song ID where I do not have any details around the song. So suppose there is a song ID song of A.R. Rahman. Okay, that has a song ID of 2. There are songs of Arijit Singh that are being having a song ID of 3. So this is kind of our root, and from the root, like there is song ID of 1, and again song ID of 2 will be stored here, and in this side we are going to have like maybe song ID 4. So when I say song ID 2 means like because this is a leaf node, that's why the song ID leaf node is being stored here. So suppose the song ID is in page 10, row 2, something like that. Similarly for the song 1, I have the information like page 10, row 1. Okay. So this is the clustered index. Now you just see this thing or notice this thing. Do we really search about the song ID while we are searching in Spotify? No, right? So what we generally search, we are going to generally search something like A.R. Rahman. right? We are going to search like A.R. Rahman or Arijit Singh. So what this tree would hold is, this tree would hold the song ID of A.R. Rahman, that it would tell that if you are referring to A.R. Rahman, then it is basically the song ID 1 or song ID 2. Okay, something around this. This index is going to hold things like that. So here it is like A.R. Rahman, and on the right side, suppose it has the details of Arijit Singh as well. Okay, so it will have the reference. Now here if you see, the S1 is having this, this guy is having the reference of uh, the clustered index. So these are the non-clustered index, and they are very very useful in terms of the searching. Like whenever we want to do a search, we cannot really make more than one clustered index, right? So in our clustered index, we always store uh, our basic row IDs, row offset, and the other details. And in the non-clustered index, we will store? We store our filter criterias. So anything like, for example, when we were even talking about this wireless or the Bluetooth, generally what happens is we put our product ID into the clustered index, and in the non-clustered index we put all our product features. So now when we search our non-clustered index, we get to know that where exactly in my clustered index I will be reaching out to. So there will be so many B trees, right? Like this will be suppose B tree 2, and this will be B tree 1, and they will keep on this thing keep on helping around this. So databases are designed in a way, like internally if you see how databases are being designed, this is the kind of optimization, be it Postgres, be it SQL Server, be it Oracle or MySQL, they are consistently doing the optimization around this only, that how exactly your heap, uh, your page, your row ID, everything can work seamlessly and in a more efficient manner. So this is one of the very important concept around the index and the type of the index, like clustered and the non-clustered index, that we should be aware of. And I hope this has cleared many concept around databases for you. And that was the video, guys. If you have any question, please post it on the comment section. I will try my level best to answer that. We'll be back in my next video with query plan and the other details, like what exactly is a journey of a query when we are executing a particular query in terms of any database, and how we can actually see it live. So in our next video we are going to cover that. Till then, stay awesome. Bye. See you in my next video.